You suddenly regain consciousness, and as your blindfold is removed, you see a masked man standing in front of you. To his side, you also see three red doors, almost shining in the darkness. The man says, "You're to choose one of these doors and make your way through it." Behind two of them are prison cells, in which you will spend the rest of your life if you choose to go through them. And behind one is a supercar with which you may make your escape. I know what is behind each door. Which one will you choose? You're speechless, but forced to make a choice, so you reluctantly choose the one on the left, door 1. You have a third probability of getting the car, and 2/3 probability of getting the prison cell. But before you open the door, the masked man says, "I am going to open one of the remaining doors which leads to a prison cell." And he opens door 3, revealing, as he said, a prison cell. I am giving you the opportunity to swap your choice and go through the door in the middle, door 2. Or you may choose to stay with your current choice. What will you do? What should you do? This is the famous Monty Hall Problem, albeit a slightly more dreadful version. The original has the car as the prize. The other two doors contain goats, a less severe losing outcome. The obvious answer is to say, well, since door 3 revealed a prison cell, the car is either in door 1 or 2 now. It's a 50-50 guess. But that isn't true. You see, the masked man opening one of the doors to reveal a prison cell is very important information. Think about it. The masked man won't open the door with the car. He must open a prison cell door, and he obviously won't open the door you initially chose. And remember, you're more likely to choose a prison cell door with your first choice. That probability is 2/3. This means that the more likely outcome to have occurred is that you chose the wrong door to begin with, and the one that is not revealed leads to the prize. To build intuition, I think it's worth thinking about a more extreme version of this game. Consider the game with not 3 doors, but 100 doors now, 99 being wrong or losing doors, and 1 being the prize door. It's similar to before. You choose a door, but now the host opens 98 wrong doors in front of you, leaving just 1 left not opened. You again have the choice to swap. But really think about it now. The choice should be obvious. Your initial choice had a 99 in 100 chance of being a wrong door, a practical certainty of not choosing the prize door to begin with. And the host will infallibly open 98 wrong doors. He cannot open the prize door. That would just ruin the game. Meaning the prize is almost certainly in the door left unopened. Meaning you should definitely choose to swap. So that's the key point of the game. The actions of the host, of the masked man, gives the player information that they can use to update their view of the game. This leads nicely into the mathematics of the game. If the maths seems quite abstract here, please stay until the end as I'll try to make it more clear with a probability diagram. This is Bayes' theorem. It lets you update your beliefs about a certain event or probability given new information. So, with the Monty Hall game, we're trying to figure out the probability of us picking the prize door with our initial guess, given that the host reveals a particular door to us. So you have your prior belief about the game, PA, in this case the probability of choosing the prize door with your initial guess, door 1. So for us here it would be 1/3. And then we get some information from the host stating that one of the doors, let's say door 3, is a wrong door. PB is the probability that the host would pick this door. The key to figuring out the value of PB is realizing that the door that the host chooses depends on the door that you choose and the door which actually contains the prize. Initially, all 3 doors have probability 1/3 for containing the prize, and you pick door 1. Say door 1 actually does contain the prize. The host will then be indifferent and pick at random between the other 2 doors, a probability of 1/2 for either. So the probability that the host reveals door 3 and the door that you chose, door 1, was actually the prize door would be the product of 1/2 and 1/3, 1/6. But if door 1 wasn't the prize door, instead it was door 2, the host will have to reveal door 3 with certainty, a probability of 1. Remember, he cannot open the door that you have already chosen. So the probability that the host reveals door 3 and door 2 is the prize door instead of door 1, which you initially chose, would be the product of 1 and 1/3, 1/3. Finally, if door 3 contained the prize, then it would never be opened, so we can just ignore this event. It would have a probability of 0. So the total probability of door 3 being revealed would be the sum of the probabilities that we just calculated, 1/6 plus 1/3 plus 0, which is 1/2, which means that PB would be 1/2. And now we also already know what PB given A is. We used it to work out PB. It's the probability that the host reveals door 3, given that door 1 is the prize door. It's 1/2. Now we have all the pieces of the puzzle, and we can simply compute PA given B, that the probability of choosing the prize door on your first guess, given that the host reveals to you a wrong door, is 1/3. It's not 50-50. The probability didn't go up to 1/2 once only 2 choices remained. It stayed at 1/3 for the initial guess. This means that switching to the only other choice remaining gives you a probability of 1 minus 1/3, 2/3. So you should switch to maximize your odds of winning the game. I think a probability tree diagram would help build the mathematical intuition, so that you know exactly why we're multiplying and adding the numbers that we are. In the simplest case, when the host doesn't reveal anything, each door is equally likely to lead to the prize. So if you initially chose door 1, you have a 1/3 chance of winning. There's no reason for you to believe that the prize is more likely to be anywhere else. Let's say you chose door 1 again, but now the host reveals to you one of the other doors. You chose door 1, so the host obviously won't reveal it, no matter where the prize actually is. We can give each of those branches a probability of 0. Now, if the prize is actually in door 1, the host will be equally likely to reveal door 2 or 3, so we can give both of them a probability of 1/2. If the prize is in door 2, the host can only open door 3, so we have to give it a probability of 1, and give door 2 a probability of 0. And finally, the opposite is true for door 3. The host can only open door 2. Now we can calculate the probability that the prize is in the door we initially picked, door 1, after the host reveals a door, in our case, door 3. In red are all the possible ways that door 3 is revealed. We can multiply going down the tree and add across branches to give us a total probability of 1/2. Of all these potential routes, the one in which the prize is behind door 1 is the one highlighted in green on the left. Again, we can multiply down the tree to give us 1/6 as the probability of this occurring in general. But we don't care about the probability of it occurring in general. We know that door 3 gets opened. We know that we are on one of those red branches. So to find the likelihood of the highlighted branch occurring in proportion to all the red branches, we simply divide 1/6 by 1/2, which gives us 1/3. And 1/3 is the result we got earlier from Bayes' theorem. In fact, we simply carried out Bayes' theorem visually. You can just as easily find the probability of winning if you take the offer and switch to door 2 in this situation. Highlight the middle branch and make the same calculation. You'll get 2/3. That was my explanation of the Monty Hall problem. If you liked it, please consider liking and subscribing. I plan to continue making educational videos